Welcome to Study Loop.
This problem we're going to talk about torque. So consider that we have a rigid object. I'm going to just draw a circle here, but it could be any rigid object. And in some place of this object, I'm going to draw here, a force is applied. Okay, let's say that the object starts rotating around its center. Okay, so there is an x that passes through the center of the object, and the object just rotates. Okay, so let's say that this force is equal to F, then the torque is equal to R cross F, where R is the vector that connects the center of rotation to the point where the force is being applied. Okay, in this case, and in many cases, the R vector and the F vector are perpendicular, so you can just write the magnitude of the torque as RF. Also, we know that the torque can be written as the moment of inertia of a rigid body times the angular acceleration. Okay? In our case, we're going to need to remember that the moment of inertia of a solid sphere is equal to 2/5, times the mass of the sphere times the radius of the sphere squared, considering that the sphere is rotating around its center. Okay. Also, we need, and finally, we need to remember that the angular acceleration is equal to the variation in the angular momentum, and the angular velocity, divided by the variation in time. So what we have is a sphere that has a diameter of 3 centimeters and a mass of 225 grams that is rotating around its center, and one point of the sphere is scraping metal, and the metal exerts a force that is equal to 0.02 newtons on the surface of the sphere. Okay, and we know that the sphere is uniform. Notice that this force is going to be a kind of a friction force, so it will cause the angular velocity of the sphere to decrease. And our goal is to find, in question A, what is the angular acceleration alpha. So we know that the torque is F times the radius of the sphere, since the radius is the distance between the center of rotation and the point where the force is applied. And this is equal to the moment of inertia of the sphere, which, as I said before, is 2/5 of mr squared, times the angular acceleration. The radius is cancelled, and we have 5F over 2mr is equal to the acceleration. Okay, so we have 5 times the force, that's 0.02 newtons, divided by 2 times the mass, which is 0.225 kilograms, times the radius, and the radius is half the diameter, so it's 1.5 centimeters, or 0.015 meters. This is the acceleration. So alpha is 14.8 radians per second squared. But notice that, as I said before, the force is causing the object to decelerate, so to lose angular speed. So even though the magnitude of the acceleration is 14.8, it must add a minus sign, so that the acceleration is actually causing the object to decelerate. So it's minus 14.8 radians per second squared. And then in question B, we have to calculate how much time it takes for the object to have a variation in the angular speed of minus 22.5 radians per second. Okay, so delta t is delta omega divided by alpha, so it's minus 22.5 radians per second divided by minus 14.8 radians per second, and this is 1.52 seconds, which concludes our exercise.